Hello, in this video I want to show the 3 points circumcenter, centroid and orthocenter of a triangle are always collinear. This I will prove in 2 steps. This is the first step. ABC is the given triangle with the circumcircle. OD is the perpendicular bisector of the base BC, and you can see this angle is 90 degrees. O is the circumcenter. AE is the altitude and H is the orthocenter of the triangle. Now I'm going to join D and H and also draw a parallel line, a line parallel to DH through O. Let us call that line OK. So OK is parallel to DH. Now you can see the quadrilateral ODHK is a parallelogram because OD is parallel to KH because both are perpendicular to the base BC, and DH is parallel to OK by construction. Since it's a parallelogram, the length OD is equal to length KH. The opposite sides are of equal length. Now I'm going to invoke a property of the orthocenter. That is, the reflection of the orthocenter about any side of the triangle will lie on the circumcircle. I'm going to prove this also. That will be the last slide. It's very important I prove this or I show the proof because I don't want to have a circular proof. So I cannot use the statement I want to prove as a given statement and then again prove the same statement. So I will make sure I prove this orthocenter reflection lies on the circumcircle. Now if you look at these two triangles, DEF and DEH, both are congruent because D is the common side, HE equal to EF because they are reflection, and this angle is 90 degrees. So both these right angle triangle are congruent. That means the length DH equals length DF. But since this is a parallelogram, we know DH is also equal to OK. That means OK is equal to DF. That means ODFK is an isosceles trapezoid. The two sides of the trapezoid are equal. Then this isosceles trapezoid has symmetry about the center line. It has almost all the properties of an isosceles triangle. That means this length, this angle DKF, you can call this angle should be equal to this angle here, OFK, because these two triangles are congruent. So these two angles are equal. Now look at this triangle OFA. It's an isosceles triangle because OF is the circumradius, OA is also circumradius. That means OFA is an isosceles triangle. That means this angle here I have shown must be equal to the angle shown here because it's isosceles triangle. Now since this angle here OAK is equal to DKH here, these two lines should be now parallel. I have shown the arrow here. That is, this diagonal DK and the line OA are parallel. That means the length OD should be equal to length AK. Now comes the most important property I am looking for. The length AH, the distance from the vertex A to the orthocenter AH, is twice the perpendicular bisector OD. So that is the first step I am proving in this slide. Again, remember the length AH, the distance from vertex to the orthocenter is twice the perpendicular bisector OD of the triangle. Okay. Now let's go to the next slide. This is where we prove the theorem. Now O is the circumcenter, H is the orthocenter. I'm going to join OH, and also I'm drawing the median A to D, because D is the midpoint, so AD is the median of the triangle. Let's assume the line AD and line OH intersect at point X. We don't know what point it is. Let's call it X. Now these two triangles, ODX and AXH, are similar triangles because OD is parallel to AH. Both are perpendicular to the base. These are opposite angles. OXD and AXH are opposite angle. That means, and these are parallel lines, so the alternate angles are equal. So these two triangles are similar. That means all the sides will be in the same ratio. I have shown it here. AX over DX, AX, okay, here, AH over OD, AH over OD should be equal to AX over DX and also equal to OX over HX. So the three sides, the corresponding sides are in the same proportion. The previous slide I have shown AH over OD is 2. The length AH is twice the length OD. That means the length AX is twice DX. That means X has to be the centroid of the triangle, because the centroid is the one that divides the median in the ratio 1 to 2. So the intersection must be the centroid G. That means OGH, all the 3 points, the circumcenter, the centroid, and the orthocenter, they all lie in the same straight line, or they are collinear. And also we see an interesting property. The ratio OX over XH is 1 to 2 because of the same similar triangle. The distance between the circumcenter and the centroid OX and the ratio between that distance and XH or GH is 1 to 2. So this concludes the proof of the stated theorem or corollary. Now let's go to I said I will prove this reflection theorem. That is, this is the triangle, this is the circumcircle. We don't know whether it's a circumcircle or not. This is let's assume Q is the orthocenter. This is the reflection. Q prime is the reflection of Q about this side BC. And we are going to show the Q prime, the reflection lies on the circumcircle of the triangle. Now, I have some construction here. I have given actually the proof you can see here. This angle, here I have shown ACQ, let's call it ACQ, is actually 90 minus A. A is the total angle here, angle CA, whatever this altitude is. We can call this D, or it should be actually D. D is moved here. The D should have been here actually, this D. And because these are complementary angles, so this angle is 90 minus A. Similarly, this angle is 90 minus C. Okay, the angle C of because it is complement to this right angle triangle. Now this is an isosceles triangle because this is a reflection and this is 90 degree, this is a common side. So the length, this angle here is equal to this angle here, okay, angle Q is angle Q prime, but angle Q should be equal to 90 minus A plus 90 minus C, which is equal to angle B. 90 minus A plus 90 minus C, I have shown it is equal to 190 minus A minus C is equal to B. That means this angle is equal to B. That means Q prime is equal to angle B. That means the Q prime and B, A, C, they all should be in a circle. That is the inscribed angle theorem. So that shows the reflection of an orthocenter always lies on the circumcircle of a triangle. So this concludes the proof. The proof looks a little bit longer to me, but I don't know if there is a shorter proof. Maybe once you see this proof, once somebody sees this proof, they can come up with a shorter proof, but I doubt it very much. You can prove it in a very in a shorter way. Thank you.